Welcome to week 11, day 1 of CSI 45. So I've been working a little bit. It's about 15 minutes worth of work here. I was starting to do, I think your next homework assignment, we skipped over Syscalls a little bit. So I'm going to actually give you a different homework assignment than the one I promised last week. I said I would do hash tables, but I think I do want you guys to get a little experience with system calls, or, you know, if this might actually be interesting for you. That's why I left it up here. So I got a number of questions over the weekend about different C++ things. So I put this together to demonstrate a couple different concepts. So this is 4th semester computer science. You can see maybe the more proper way of doing things. So in your homework assignments, we were using the C library to get the time, and that returns... there's a couple different ways of doing that. This is the C++ way of getting time, which is in the Chrono Library. And so some of you guys have been getting negative times for your runtimes on the image filters. So if you want to learn how to use the proper way of getting the time, I will show you right now. It's the hashtag include Chrono Library, and you do so like this. You can actually using... If you want, you can use namespace chrono will work. Might be stood chrono. Yeah, shoot. Yeah, it's not really that quite yet. Okay. All right. So this is a better way of getting the time on something. So you can. You should be able to get rid of this. What is it? 6, 8 letters. Get rid of all the extra colons everywhere. Okay, so the Chrono Library is found in the stood : chrono namespace, and so if you use namespace stood, use namespace chrono, then you don't get these really obnoxiously long function calls. Like if you want to get the current time, and this is why I don't teach it too often in earlier classes, it's stood : chrono : steady clock, or there's other ones. There's system time and high performance timer and stuff like that. Steady clock or high performance, high resolution timer are the ones that I use the most often. Steady clock can't go backwards, which is nice. But it's an obnoxiously long function name, right? So imagine trying to teach a CSI 40 student stood : chrono : steady _ clock : now. Now it's 3 letters. Now it's 3 letters. The rest of it is obnoxiously long, though. So by importing the stood and chrono namespaces, we can at least, what's that? 5 plus 8 sounds like 13x. Yeah. We can at least make it like this, and then it's less obnoxious. Okay. And so that is going to get the current time. So, in all seriousness, though, despite me sort of mocking the verbosity of modern C++, it is better. It is superior to the C way of doing things. So, time is the way of getting seconds since the beginning of time on January 1st, 1970. And... clock is it returns ticks, and it's in a special type called clock T, and there's a constant called clocks per second, which is always the same value under the POSIX standard, so it doesn't really need to be a constant, but it is. So clock just basically is kind of the equivalent of now, but doesn't necessarily give you the same resolution. A high resolution timer will give you better resolution, equal to or better than clock. And what's nice about this is you can get a duration in different formats. In this case, I'm going to get a duration in double format, which means that it just gives you the time duration in seconds with decimals. You don't have to divide by clocks per second and all this other stuff. And the implementation is probably better as well if we turn this to be int. Then you'll it doesn't like that. Okay, that's fine. There. So that's how you would do it using C++. So steady clock now. If your filter is implemented Chrono into your code and you got one negative time, still, I don't know what's going on with your code, dude, honestly. Like, clock shouldn't give you a negative result either. I don't know. I won't tell you. So yeah, if you corrupt the call stack, or if you corrupt the registers, should not be corrupted, then let's take a look at it. Why not? Sepia. All right. So, what do we got here? We got no push statements. Yeah. So yeah, you got no pushes in this. Okay. Student custom.s. Yeah, same thing. There's no pushes or pops here. So if you corrupt the registers, then that'll do you. Well, I mean, this code's wrong, right? Because like you're editing R5, and so that's going to change whatever R5 is in main, and so whatever value, because main expects R5 to be the same when it calls this function. So when it comes back, R5 is a different value. You've broken main, so you're kind of in R5 is changed, R6 is changed. Yeah, so you're kind of in undefined behavior territory at that point. Yeah, at least if you push and pop, then you know it's not you corrupting registers and stuff like that, right? So, yeah, if, for example, the current time is held in a register and you override it somehow, then... Yeah. Okay, so let's go back into here. So, yeah, always start off your functions with pushing and popping. Don't optimize the pushes and pops out unless you're literally not changing any of the variables from R4 up. Right. So that's C++ way of getting the time. Okay, so there's some other C++, modern C++ magic going on here. So this is how you generate random numbers using C++, and there's different ways of doing this, all of which are kind of garbage in my opinion. Sane programming languages just give you a rand function that will give you a good random number without any headache whatsoever. And Python, I think, is just called rand. Yeah. Or random. Example code, please. Example code. Call random. There you go. Random gives you a number from 0 to 1. You can call uniform distribution to get a number in a range. Random range 0 to 9, right? So it just has, you just call a function, you get a random number. Like, this should not be a hard thing. And C++ has two options for you. One is the C way, which is simple and easy to teach, and the other way, which is look it up on CPP reference every time and copy it over, but better, technically. And to me, that's not good library design. As Bernie Strustrup once said, libraries should exist to make common tasks easy, especially common complicated tasks like making a random number. Making a random number is actually not an easy thing to do. It should be easy on the programmer, call random, you know. But it's not. So what this is doing here is this is making a default random engine. That is the engine that will be used to generate the random numbers. Usually I'd use Mersenne Twister 19937 there, but I wanted to be a little more readable for you guys, I guess. And then this is creating what we just saw in Python, a uniform integer distribution. The numbers we get out of this will range from 0 to 10 million. So we can get 0, we can get 10 million. It'll be an integer. Cool. And then bind is some C++ magic. So the distribution function, this actually creates a function kind of, and you pass it a generator, and the generator is the random number generator, and then that plugs into the distribution object, and the distribution object uses the generator to generate a random number in the range 0 to 10 million. It's kind of ridiculous. Bind will put the two of the things together. It basically makes a new function by binding a parameter to a function object. And so what we have here is just a function called roll. And so if I were to uncomment this, well, let's make this 0 to 99. A couple rolls. So you can see that it will just roll 4 numbers from 0 to 99. It's actually, when you're done with it, it's fine. You know, like you just call roll. Cool. And it just rolls a number from 0 to 99. Easy. You know, the obnoxious thing is just how verbose it is, you know. And in C, if you use a C library, which is technically inferior in every possible aspect you can measure it on, very easy to seed the random number generator. You can seed it to the current time if you want, or not. But you just call, scout rand modulus 100. And so it's just a function that just returns a random integer from 0 to some large number. Maybe not that large. Technically, rand doesn't have that big a cap. Rand in the standard, man 2 rand, man 3 rand, sorry. And so rand max is the maximum number generated by rand, and the POSIX standard, I believe, only specifies a minimum of 32,000. So the rand max might actually be a very low number. In general, though, it'll give you a full, rand max is assumed to be 32,000. That's not a lot of randomness. If you're making a blackjack game for online play, you don't want there to be only 32,000 possible, numbers rolled. So, in reality, rand max is usually the max int. That's still not very good, honestly. It's not very good. So, the rand function also has patterns and lots and lots of deficiencies, but the good news is I can teach this to a CSci 40 student in a minute. You know what I mean? Like, just make some random numbers, easy. Maybe from 0 to max int, right? That's easy to teach. srand, rand, easy to teach. This garbage, trying to explain functional programming to a new programmer. Good news is, I hear that the standards committee is working on better random number generation that isn't idiotic like this. This is a giant wall of text to Yeah. Get us to where C is, where C was 50 years ago. You look at Dulio's code, you had to push pops correctly, it still gets negative time. Alright, sure. CD sm edge. Then student, which one? Custom. S. Push, pop, pop. Got some multiplies, got some other stuff going on. He's calling S custom. Then main.cc. S custom. LF student underscore custom. Define student underscore custom. He's still linking the other ones together. Customs here. All right. Should be fine as long as they're not doing anything to break the code. Yeah, look at this. This is what annoys me. Look at this type here. Look at that type. My lord, you know. Stood : chrono : steady clock : time point. Auto. Stood : chrono : duration cast. Stood : chrono : microseconds. In minus begin dot count. Like, I mean, am I like, am I out of line here, or like is that just like really verbose to get a duration? You know what I mean? Yeah, it's like somebody like who grew up programming Java was like, you know what we need in C++? We need more typing. That's what we need. There's not enough typing in C++. People are able to write C++ without breaking their keyboards and wearing it out. So I'm just gonna like that. Like, look at the size of that damn thing. You know, I just want to print out the difference between end and start. Things like bloody almost the entire width of the screen. All right. Divided by, yeah, so I would use what I just showed you there, Delia, as a less verbose way of doing the same thing, but you'll see this on like CPP reference for sure. Divided, and see it's got the division in there. All right, so do it again. Stood chrono steady clock now. If def student darken lf s custom else end if end darken time. Yeah, it shouldn't be negative. It should be impossible to have a negative number come out of... you are using steady clock, right? Yeah. Do we just do a fresh make, clean, and make? Yeah. Yeah, I'm just doing make, clean just to make sure there's anything weird going on. Now you gotta feel the burn of CImage, the CImage header library. If anybody wants to go through there and cut out the pieces that aren't used. All right, so what we got here? Doing student darken, student custom, neon, student darken, linking them all together, including the pieces we're not using, right? Okay. I don't see any negative numbers, dude. Don't know what to tell you. Worked fine for me. I don't know. I just ran it. I don't know, man. I don't know what to tell you. I can't make code not work right. I'm kidding. Yeah, I don't know, dude. It might have been the make clean and the make. Like if you had an outdated object file in there somewhere, I don't know. So it's best I can tell you. Okay, so yeah. So do you guys understand this for making random numbers? These 3 lines make a function called roll that generates random numbers from 0 to 10 million. 1 to 10 million? Yeah, fine. We'll do 1 to 10 million. So it feels weird to me to do 0 to 10 million. It should be 0 to 99,9999 or 1 to... Okay. Yeah, so yeah, you don't need to Google it, just use this and change these 2 numbers to whatever range you want to generate random numbers in. And probably change default random engine to Mersenne Twister. Arguably, if you want better random numbers. It should be fine though. Okay, and then what else we got here? So now we're gonna make an array holding all the random numbers so we can feed them to both. So we'll use the same random numbers for both C++ and C implementations. I'm indenting this. Okay, so what does generate do? Generate calls the roll function on each element of R. So you could do the same thing here. Generate, like, there's some standard library functions like for each that you run. It'll pass each element of the array to a function. It's like you just write a for loop for it, man. Like I don't need a standard library function for it. Generate is essentially the same thing as this. For every integer by reference in R, x is equal to roll. It's actually less typing that way. Yep. Okay. So that's what generate does. Why use generate then? Why use generate? You don't have any ideas? We're talking about modern C++ here. You're getting into modern C++. In elementary school, when you're learning arithmetic, you're learning like Babylonian math and angles and stuff like that. It's all Babylonia. You got into algebra, it's like medieval Arabic math. Then in high school, you do calculus, you're talking about Leibniz and Newton in the 1600s. Now you're up to 2011, 10 years ago. So you don't have to loop. There's a loop in it. In fact, generate is probably going to generate the exact same code I showed you right there. It's probably just a range-based for loop. Maybe using iterators directly, maybe not, but generate just basically does the exact same thing I showed you. And the thing that I showed you is less typing than generate, so why use generate, right? Like this is actually shorter. It's shorter to write. So why use generate? Use this because it looks professional? Possibly. Yeah, that's actually a good answer. If you do that on a job interview, then the people go, oh, he knows Mono C++. What a fancy individual he is. It looks easier to write. Yeah, I mean, no, I mean, I don't know. Like, that's pretty easy to write. You know what I mean? Like, for every element in the array, set the element to be the result of roll. I don't know. Less job security. I don't know. Maybe. The reason why you'd want to write generate, there's two reasons. First of all, it expresses your intent better, right? It expresses what you're trying to do. Generate is typically, but not always, used to fill an array with values. So so there is, you know, like, let's say you wanted to fill an array with the numbers 0 to, 99999. There's a function for that. It's called iota. r.begin, r.end fills the array with 0 to 99,999. So there's a function for it, So you all of you guys could write a for loop that would just set the value of an array to the index of the array. You could all do that in your sleep, I'm sure. But iota expresses the intent of what you're trying to do to two people. First of all, to the compiler, and second of all, to anybody reading the code. Anybody reading the code looks at this and goes, "Oh, iota, he's generating an array that's filled with different numbers, for whatever reason." Sometimes we'll zero fill an array. Sometimes we'll fill it with each number being different. We'll do that, for example, if you need to make ID numbers for a marathon or something. So each person will get their own unique ID. You'd use iota for that. Easy. Or if you wanted to fill an array with random numbers, also very common. When you're testing code, you don't want to test your code on just zeros. Insert 0, search for 0, delete 0. It's very boring. You're not even going to know if your code's right or not. So it's very common when testing code to generate a random array. And generate array begin, array end, roll is a way of expressing that. And if we have ranges, we might even be able to do it even more concisely in C++ 20. If you guys want to see that. I don't know if ranges are installed on the Raspberry Pi, but I can show you on the real server what ranges look like if you guys would like. You like the look of generate? Yeah. The other thing is people reading your code. People reading your code. It's expressed intent to the compiler, so the compiler might do different things with it because it has more knowledge of what you're trying to do now, right? If you do a for loop, all it knows is you're trying to do a for loop, right? But if you're like calling iota, and let's say you do some things with it, the optimizer actually has a higher level view of what you're trying to do, and it might be able to generate better code as the result of it. Second reason why. So first reason is it expresses your intent. So this means generate an array filled with random data. That's how to read that in English. Generate an array of random data. And this means, fill an array with numbers from 0 to 99999. And iota can also, if you want to start at 1, you can do that. And then it would fill the array with the numbers from 1 to a million. Who the hell is texting me over and over? Mute. All right. So that's the first reason. It expresses intent. Second reason, what if someday C++ had the ability to automatically parallelize your code? Parallelizing your code means you've got 4 cores on the Raspberry Pi, and it would be like, all right, you're generating you're generating a random array. There's no reason why only one core needs to be involved in this. Let's have all 4 cores involved. And so if in the future, I don't think it does it right now, but if in the future C++, the optimizer would be like, hey, automatically parallelize code, then you might run it and find that it's just 1 day 4 times faster. You know what I mean? And so it's going to be easier for that to be parallelized than a for loop. For loops, there's OpenMP, which allows you to parallelize for loops and things like that. But you don't even have to install OpenMP or know anything about OpenMP. Just someday, the authors of the standard library themselves, do you guys understand? Because the authors of the standard library can actually say, hey, if this would be beneficial to parallelize it. So when you call generate will be like, all right, my array is only 10 big. Nah, who cares? It's way too much overhead to parallelize. So it'll just do a little roll the dice 10 times, fill it in, be done. But if you're trying to fill a gigabyte of RAM with random data, then the standard library authors who have spent a lot of time thinking about this and benchmarking things and stuff like that could be like, all right, it's going to be beneficial to parallelize our code here. And then it will spin off another thread, 2 threads, 3 threads, whatever they've decided is optimal for your hardware and for the problem size. And just one day, your code just might be 4 times faster. And you're like, oh, that's cool. Neat. Do you guys understand? So they're starting to bake parallelism into they're starting to bake parallelism into C++ itself. Proposal 2015. And so you can set what are called execution policies and awesome. Thanks, CPP reference. And that's currently in a technical specification. So that, like I said, this isn't, this isn't really hypothetical, but it's also not out yet, right? So experimental execution policy. Sounds like the king is going to execute somebody experimentally. Put them in the wheel of pain. The experimental execution policy. So, yeah, so that's the thing, right? And so you might be able to specify when you do a generate, you would specify, hey, parallelize and vector. Hey, you guys know what that means now, right? What does the vector mean? Anyone? Parallelize plus vector. VFP, yeah, neon, right? So automatically generate SIMD code for me, neon, right? Code for me. And so the for each function would have a new parameter, I believe is the proposal. And the new parameter to for each, which is not even in the wiki yet. Let's see, transform reduce would take a execution policy. And so the execution policy that you pass to it would be run this in serial, run this parallel, run it in parallel, and vectorize. And so you'd be able to choose yourself if a function runs in serial or parallel, but feasibly someday, if you do that, then it would call the standard library, and the standard library might just be like, hey, we've got parallel stuff, let's just parallel it. And so that's, it's more likely that would get an easy pickup than a for loop. Although someday, maybe the compiler will parallelize a for loop for you automatically. Right now it requires something called OpenMP installed. Okay, so is there anything else in here? You guys wanted to see ranges, right? So learning points for today. Random is a better but way more verbose way of making random numbers. Chrono is a better but more verbose way of getting the time. What was the other thing? Generate a random function. Generate to use to generate the random array for testing input. Testing, so IOTA can be used to generate a bunch of IDs. You could easily write code to do number 3 or number 4. It's not number 3 and number 4 are not going to change your life. You could do that just without knowing it. You just write a for loop. 1 and 2 are definitely things you should start using, in my opinion. Like, you're advanced enough now that the reason why I teach rand is because it's literally a function call. It gives you a random number. It doesn't have that cognitive load, is the technical term for it. That, like, imagine like having that on a midterm, right? Write code using Chrono, closed book. You're in a giant lecture hall. Write code in C++ to generate a random number. It's like, how confident are you you're gonna get all that right? You know, versus rand. You know what I mean? In a first semester class. Your 4th semester now, you can probably be okay with the better stuff. Okay? You guys with me on this? And this you can cut down on the verbosity by doing that. And Dolio, I would do a duration that way instead of duration cast and division, because see how there's no division here. I don't have to know how many ticks it is. Yeah. So a lot of C++ professors don't like this. They like the verbosity. I can only assume it's because they learned Java. Where verbosity is not just the way things are, it's a way of life. So you could easily write code to do 3 or 4, but it expresses intent and might open up discussions. Okay, you guys cool with that? Yeah, the duration casted is microseconds, yeah. So then, yeah, you would always divide by 1,000,000 or whatever. But, I don't know. Why do a division when you don't have to? All right, so let's take a look at ranges. Let's see if ranges are even installed on here. All right. Googling CPP reference ranges. CPP reference ranges, and it gives me kitchen and bathrooms. Come on, guys. I know it's new. It's not that new. Come on. It's been out for a year now. Okay. So let's even see if it's installed on Raspberry Pi. Include G++ -- version. Oof. We're 2, almost 3 versions behind of G++. All right. Let's see if this will work. Nope. Okay. So the Raspberry Pi is always behind. So normally in this class, you guys would be given a Raspberry Pi for the semester, and you would learn how to do this kind of stuff. Instead, I'm just going to show you. So in order to install software, you use sudo apt install for Ubuntu systems. So there's many different versions or flavors or distributions is what they're called of Linux. I use Ubuntu simply because it has the best support. A lot of people like using Arch or obscure distributions. I like having distributions that have documentation available for them. So I learned that lesson a long time ago. I bought a video card that was not either an AMD or an NVIDIA card because it was cheap. Yeah. And then good luck finding games that supported it, you know what I mean? So, okay, it doesn't have G++ 10. Fine. G++ 9, do you exist? Alright. Python, Clang 9? No. What version of Clang do I have installed in here? Clang is at version 9. Let's see if Clang can install that. Or, did I delete ranges out of that? I probably did. Nope, not installed. Yep, all right. So the Raspberry Pi is always behind the standard distribution. So let me log off the Pi. Let me just show you some stuff with the ranges. It's pretty cool stuff. Then ranges.cc. Thank you. All right, so let's go get some sample source code. They're kind of neat. So the thing that I like most about ranges is that you don't have to do the begin and end thing all over the place. Instead, well, okay, so there's a couple different things I like about them. The first is it has the pipe operator. So if you guys have ever used Unix and you've ever like said cat ranges, pipe through, sort, you know, something like that, it'll sort the lines alphabetically, you know, pipe through, word count, or whatever. So that notion of piping the result of one operation into another operation is... Are you guys familiar with this, by the way? Has anyone not used the vertical slash IE pipe character in Unix before? Unix-like systems, whatever. Unix is a copyrighted trademark of Bell Labs. Yeah, whatever. All right, so maybe let's do that. So there's all the students logged in. Pipe through cut dash field 1 dash eliminated by space. Boom, there's and that's not their full name, so that's okay. The full username. So that is cutting just the first column out. If you want to cut the IP addresses out. Oh, sorry. No. Their terminal that they're on, whatever. I can do it that way. Let's just get their usernames, and then you'll notice the first two lines are not used. I can use tail. Plus 2. Pipe through tail plus 2. Will that do it? Plus 3. There we go. So I don't want to have that space. I don't want to have user on there. Those are not valid usernames, so I use the tail function, which gives you the bottom lines of input. So in Unix, there's all these utilities that if you just run them by themselves, like, they don't seem to do anything, right? It just opens up a screen, and if you don't know Control-C, you're stuck, and you've got to quit PuTTY and relaunch it because you're stuck in it. And it doesn't seem to do anything, which seems baffling at first. But what you have to understand is that all of these utilities read from the standard input, and they write to the standard output. And when you just run them by themselves, they don't seem to do anything. Now, if I close the file, Control D is the end of file character. Boom, that pastes. That finishes, and then tail outputs the last 10 lines by default. That's what tail does. Useful if you have a log. Locate HTTP D, pipe through grep log. See, I'm using pipe. Logs. All right, let's see what that is. Vim. Okay. People trying to log in on my server and failing. So if I tail that file, then that prints just the last 10 lines of it. Very common with log files. Locate log pipe through. Oh, I don't have HTTP on here. Yeah, but yeah. So if you just want to see the last couple lines, you'd use tail. Anyhow, so we got these people, and I'm cutting the first 2 lines off, and I got their usernames, and then I want to put them in alphabetical order, so I pipe the results through sort. There you go. You can see Min, Corelli, and Thompson are logged in twice, though, so if I pipe that through unique, it will unique the names and eliminate the duplicates. And if I pipe that through shuff, it'll randomize them. So the Unix philosophy is to have a simple utility that does one thing and does it well, and reads from standard input, writes to standard output. That's the Unix philosophy. And ranges have that same philosophy. And so what happens when you do this is W, which shows who's logged in on a server, sends its standard output rather to the screen. It sends it to cut. Cut is used to take vertical cuts of a file, of an input. Like imagine in Excel how you could select column 4 in Excel. It's like that. So I'm cutting out just the first. Field, the usernames, and then that would normally print to the screen. But rather than it printing the screen, I'm piping it into tail. So tail reads from standard input. It thinks it's reading from the keyboard. It's not. It's actually reading the input from cut. And so tail reads from the standard input, and when it hits the end of file, it prints out just the bottom 10 lines of code. In this case, it's printing out everything except for the first 2 lines. So starting on line 3, prints everything else. I'm using that to clip the top 2 lines off. And then sort thinks it's reading from the standard input. If I type sort B A C and hit Control D, you can see that sort sorts whatever gets on the standard input and it prints it to the standard output. But sort, it's not getting to go to the standard output either. That goes to unique. And unique reads from the output of sort and writes to the input of shuff, and shuff reads from the output of unique and outputs to the screen, and there we go. And so this is all the usernames sorted, unique, shuffled, blah, 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 blah. And so that philosophy allows you to write very powerful commands very, very quickly. If I want to generate random numbers from 1 to 100, boom, there we go. Sequence can do that. Pipe them through shuff, boom, I got random dice rolls, or whatever. Not exactly random, but, guaranteed no repeat random dice rolls. Very easy. Boom, boom, boom. All these things would take 5-10 minutes to do in C++, maybe more, depending on how good you are. Just that. So, Figlet, hi. Figlet, hi. Pipe through lolcat. Colors. Fortune generates random fortune. Fortune pipe through cowsay. Okay, that's the philosophy. All pipe is output of the last is input of the next. Yes, it uses a system call, and that's one of the things I wanted to get to today. So perfect. There is a system call called dupe. And what dupe does is it will duplicate a file descriptor. So in system calls and in C, in system calls, there's 3 different types of I/O that you guys kind of have to know. The first is operating system level files. When you open a file at the operating system level, it gives you an int. So if I try opening a file and it succeeds, it's like, here you go, it's integer 5. And so when you write to a file, you're writing to integer 5. And when you read from a file, you're reading from integer 5. Standard in, standard out, and standard error are 0, 1, and 2. The C library has a wrapper on top of that because the read, write, and open functions in the OS are obnoxious. If you remember when I tried doing it from memory, I forgot one of the bit flags would actually allow you to read from it because I hardly ever use system calls to read and write to files. I've done it a few times, actually, about a year ago in serious practice because I was trying to... I had a program that was not running fast enough for me, And so I wanted to see if the problem was with IO streams, the C++ way of doing files. And so then I rewrote the C++ way with IO streams. I rewrote it 3 times. I rewrote it using modern C++, using the format library, which maybe we can talk about today or maybe not. I rewrote it using the C library, using fopen, fclose, fprintf to read, write, and open files. And then I rewrote it using the system calls. And none of them seemed to really make much of a difference. So. IO streams is definitely the slowest though. But you can speed it up, and I did, so that it was roughly equal in time. The fastest way actually was using none of those. The fastest way was not using any of those approaches. The fastest way was we haven't had that discussion of how memory works in hardware yet. It's using memory mapping, but we'll have to save that for another time. Okay, so anyhow, dupe. What does dupe do? So dupe, you pass it a file descriptor. For example, let's say that you open a file and the file descriptor is 5. And, okay, so you can close the file descriptor also. And by the way, you can close the keyboard. You can close standard input. That's fine. Standard input 0. There's a function called close, man to close. So you pass 0. You can't read from the keyboard anymore. Congratulations. Why would you want to do that? Well, what happens with a pipe is this. It closes standard input. It has, let's say, file 5 open, file descriptor 5 is open, and then it calls dupe. And dupe allows you, it'll actually pick the first open file descriptor. So in that case, it would dupe the file descriptor to be file descriptor 0. Okay? So now when you read from file descriptor 0, you're actually reading from the file instead of from the keyboard. Why does that? Why would you do that? Dupe, if you just pass in a file descriptor, for example 5, then it finds the first file descriptor that's available. If you've closed the keyboard, then it will be file descriptor 0. Otherwise, you can specify the file descriptor that it dupes to. Okay. And so reading and writing to 5, reading and writing to 0 is exactly the same. It's a duplicate file descriptor. Now, and you don't have to call close if you use dupe 2, by the way. So if you just say dupe 5 to be 0, the keyboard's closed, 5, the file that you have open, can now be read from file descriptor 0 as well. Why does this matter? Because we're talking about system calls today, and this is cool. And we're talking about ranges. So we're talking about modern C++ 20, and we're talking about ancient, primitive, no system library at all. Directly talking to the operating system. So we're talking at two different extremes here. Same concept. So how does a program run? How does a program run? Will there be a Unix portion on the test? Yeah. The next midterm will be next Thursday, by the way. So how does a program run? Well, that would be the last step. In our last lecture, yay, it all ties together. Look at this. Okay. So when you link things together, you build an executable. And if you have dynamic, thank you very much. If you have dynamic linking, remember some of those functions aren't actually linked into the executable. So there is the final step that we didn't get to last Thursday called the loader. And the loader, will, when you launch your program, if there's still any missing functions in it, then it will find them in the standard library. There's something called a DLL in Windows, or a shared object, a .so file in Linux. And so if I nm a.out, you can see that there's still some undefined functions in here, but it linked fine. It linked fine because they're in the standard library. And by default, GCC will use a shared standard library. And so when you run the program, there's still some undefined functions in there. GXX personality V, found in CXX ABI 1.3. libc start main, found in glibc version 2.25. Stack check fail, found in glibc version 2.4. So when you run the program, there's something that's called the loader that runs. And the loader finds all of the missing things in these DLL files or .so files. They've got compiled code in them, and it pulls them in, finally makes the executable ready to run. Then what happens? Then what happens? This is good talk, by the way. Yeah, this is really talk. I like this one a lot. What happens? How do you actually run a program? Could you guys write a program that would run a program? Do you guys know the system function call? Midterm during spring break after. When we get back. Look, I have a program that runs Vim. Cool. That's neat. Or inside of here I could say who, pipe through, sort, pipe through unique. When I run it, it runs that whole complicated Unix command. Okay? Super easy. However, that's not actually launching a program. It is, but what happens when you type Vim? Does the old program go away, or is the new one still running at the same time? What program are you running right now? Who am I? What am I doing here? What is my name? What program is running right now as I'm typing right here? Who's accepting those keystrokes? What's the name of that program? What's happening? I'm freaking out, man. There's obviously a program running right now, right? I'm hitting keys and letters are appearing on the screen, and if I type something valid, it runs a program, and if I don't, Vimu, it says there's a program running right now. What's the name of that program? Bash? Good guess. TCSH, correct. Who am I? Ben TCSH. That's the name of the program running right now. It's just a program. There's nothing special about it. You can actually set any program to be your shell. For example, if I wanted to, sudo vim etc password dolio. You're not found? You don't exist? Oh, wrong server. Okay. Sit down. Is Muya on here? Okay, so Muya, right now your shell on the main server is TCSH like all normal people. I'm going to change your shell to be Vim. All right, so please log in on the main server now and share your screen. Are you going to expose your password? There's no passwords in the password directory, the password file. Used to be there. That's why it's called the password file. Everyone's password is X. It's very highly secure. Right? So yeah, it's in the shadow file. So Muya is sharing his screen now. Watch.
You mean like the main server, like
Yeah, the one for not the Raspberry Pi, not the Raspberry Pi. And so when he logs in now, he actually doesn't have any access to typing ls and cd. When he logs in, it's literally a Vim. And then now, I actually was able to hack. Oh wait, am I recording? I once got access to an account that had just Vim access. Now, Muya, if you type exclamation mark colon, hit colon, type exclamation mark, and type ls. Yeah. See that? You can run a shell from inside of Vim, and so I was able to run a shell from Vim. So type /bin/tcsh /bin/tcsh and hit return. What happened there? Seemed like it worked for a second. Anyhow, you can shell out of it, and then yeah, change your shell back. I'll leave that as an exercise for the reader. Okay, so you can change your shell by using change shell, and so do that. Hit exclamation mark chsh change shell chsh.
I'm literally.
And just hit return. Error when processing command line, non-editor command. I might be remembering that wrong. I'll do it for you. Okay. Or I'll just edit the password file again. Anyhow, the reason why I'm torturing my TA like that is because I'm trying to show you guys there's nothing special about Bash or TC shell. It's just a program. It's just a program. So how does TC shell launch a new program? Because system, when you run system, it runs the program, then it comes back. It's not very useful. So how do you fork yourself into two different programs? What do you guys think the system call to fork yourself into two different programs is called? :sh? Yeah. I haven't done that in a while. :sh, yeah. Okay. With a space after the exclamation, yeah. I haven't done that in a long time, but you can. If somebody does give you a restricted shell that only has Alpine, which is what happened when I was hacking this one company that my friend was working at for fun. Let's say with their permission. let's say all they had was Alpine accounts. That was the shell. When you logged in, it would just pull up your email. That was it. But Alpine allowed you to set your text editor to VI, and so I changed my text editor to VI, and then from VI, I launched a shell, and then was able to change my shell out from Alpine and had a full account on the system. True story, or is it? I don't know. Depends if the FBI is watching or not. So, the hacker man, right? So how does one program become two? Like, your TCSH, somebody types Vim. I can background this, right? There's two programs running at the same time, right? Well, I've got multiple Vims, I guess, running at the same time now. But if you type PS, you can see the processes that you're running. There's TC shell, which is my login shell, and it's running PS right now, and I've, I guess, backgrounded Vim twice. Let's quit out of one of them. There you go. So you can see I got 3 different programs running. So how do you fork a program into 2 different programs? What do you guys think? If you had to create a system call that would fork a program into 2 different programs, what would you call that? What would you call that system call? Fork. Let's find out. Survey says, nope, no fork. Oh, fork. It's called fork. And so if you run a program in C++, just call fork, and it makes a brand new program. And that program is the exact same program that you're running right now. It actually duplicates the program that you're running right now. And so if you want to do parallel processing with one easy step, call fork once. And then the return value of it tells you, are you the parent or are you the child? Okay, so if you are the parent, it returns the process ID of the child. If you're the child, it returns -1, something like that. -1 is returned to the parent on failure. Yeah. 0 is returned in the child. So if you get 0 as a result here, then you are the kid. If you get -1, an error occurred. Otherwise, it will give you the ID of the kid. So then main.cc. So how do we make babies? All right, you use fork to make babies. Okay, so auto ID equals fork, and if ID equals -1, cout could not fork by exit with an error code. Otherwise, if ID equals 0, cout I am a child process. Else cout I am parent process. To make a baby, you have to fork. That is correct. Sounds great until you have to kill a child with a fork. Fork does not return a file descriptor. It is not. It is not opening a file. It is returning a process ID. If it's all going to come together, trust me. Okay. So done, and then you can call wait on the ID. So that will wait for the and to wait. I don't care. You can have the parent wait for the kid to finish. It's very common if you're going to spawn 10 kids. You spawn off 10 kids, have them do their things, and the parent will just sit there and wait on all of them. And then once all the kids are done, then the process terminates. But this will terminate. This will show you guys the process. Oh yeah, it's all coming together. All right. So when you run it, I am parent process. I am child process. Okay. While true. Infinite loop time. Look, they were alternating and then they weren't. See that? Sometimes you get 2 parents printing at a time, sometimes 2 childs printing at a time, sometimes it alternates, sometimes it doesn't. You guys see that? It's literally 2 different processes just running at the same time. They're both outputting to the same screen. And the reason why they're outputting to the same screen is because they have the same file descriptor. When you fork a new process off, it inherits all of the file descriptors, all the ints that are open on the parent. And so both the parent and the child are writing to the same. They're both writing to the same file descriptor, the screen in this case. Okay. Am I putting out an announcement for the study session? Did it get approved, Moya? 3 o'clock on Thursday? Okay, it's out. Okay. So, how do we do pipes? You guys almost have enough to know now. There's one piece that is missing, and that piece is called exec. Okay? So exec turns the current process into another process. Okay? And so what happens when you do a pipe is the shell will do something like this. When it's in the child process, let's see, when it's going to do this. It's going to close the child. Yeah, the child's not going to read from the keyboard, so it's going to close the keyboard. or we just use dupe 2 if we wanted. So if we've got a file open, let's say we've got a file open. We don't right now. Let's just say we do. We could do dupe 2. Let's say file descriptor 5 is the file we have open to 0, and now we exec sort or whatever. This is not valid syntax, but that's the general idea. So what happens is the shell will set the it'll close the keyboard of the person that has the data being piped into it. So it's not going to be reading from the standard input. Instead, it's going to be reading from a file. What file? Well, the file that the other guy is writing to. And so, and then once it does that, when it execs the program to run, the exec program inherits the open file descriptors. And so this guy thinks he's going to be reading from the keyboard and writing to the screen. He's not, because we have duped the file descriptors. We've duped him. And then the same thing on the parent process. The parent process, in this case, is still going to be the shell, but let's say you're doing a, I don't know, cat or something. So cat's going to be outputting a file to the standard output. Same thing. Let's say you have a file open, and that file opens 10. Then you dupe it to the standard output, and then it will exec, cat or whatever. Again, the syntax isn't correct. It doesn't matter right now. And so what will happen is cat is going to be writing. It's going to be was it reading? No, that's standard output. So yeah, no, we'd want to do this. So we'd want it to be writing to this file, and this file would actually be what's called a pipe file. So it's actually just used to connect two different programs together. So cat would be reading from a file. So cat's standard input would be a file. We'll say is file descriptor 10, and it's going to be writing to its standard output. Is going to be writing to file descriptor 5, and sort is going to be reading from file descriptor 5. And the beauty of this system, is what's the difference between the old one to the new one? Yeah. So this is the file, and it will become 1. And if you have file 10 open, that becomes 0, which is your standard input. So it's going to, so the beauty of this system, and the shells do this, you don't even have to worry about it. The beauty of the system is that when you write a Unix utility, you just read from standard input and you write to standard output. And when the user types one of these piped commands together, the shell just basically does this. It sets it up so that the standard input of cat is coming from a file. The standard output of cat is going to a file. In this case, it's a pipe, maybe a named pipe, or just a unnamed pipe that it writes to. And when it writes to this file descriptor, it's going to be reading from that file descriptor here. And so sort, all it thinks it's doing is reading from the standard input. Cat thinks all it's doing is writing to the standard output, but what happens is the standard output is actually a file, socket, or a pipe. And sort, what it thinks is the standard input is the other end of the pipe. And it just works beautifully that way. Okay? So that is where babies come from. Okay, that's how you make a new process. When you log in, there is a root process that runs when you log in. And it spawns off whatever is in your etc password. So when you log in, there is a systemd is what it is on this system, for better or worse. When you log in, it reads this file and says, "Oh, your shell is bin bash." So when you log in, it forks itself. And it calls fork exec. It sets up the original standard input and standard output to be the screen and keyboard. Everybody actually gets their own screen and keyboard. You can see TTY stands for teletype device or something like that. Teletype something. But basically, this is your keyboard. And so there is TTY0, and it's like that. it doesn't really matter. But basically what happens is that the first time you log in, systemd process 1 forks itself, sets up the standard input to be your keyboard, the TTY, sets up the standard output to be the screen, the TTY, and sets up standard error to be the screen, the TTY. And the TTY is a file that when you read and write to it, it's going to appear on the screen. You can actually echo things into the TTY file, and that will actually cause things to appear on your screen. The teletype device, it does look like that. But even though nobody's used a teletype device in 50 years or something, I'm sure there's still, some in existence somewhere, but the industry has not used these things in forever. This is how you used to log into a mainframe, by the way. So you'd connect to a mainframe, and it'd actually print out, please enter your username. You type in your username and hit return. And then the teletype, it's called a teletype because it's a typewriter that works over a telephone. That's why it's a teletype. And so you hit return, and it sends the keystrokes that you typed to the mainframe. And that's why, by the way, it doesn't send anything until you hit return, right? Because it's wasteful to do it until then. So you type in a bunch of things, you hit return, it sends the whole string over to the mainframe. The mainframe process it. It's a okay, username, acknowledge, please enter the password. You type in your password, hit return, goes to the mainframe. Mainframe writes back, congratulations, you have logged in. ls, return. Here are the files in your directory. And it just sits there spitting out paper. And so that's how it used to be. And the original organ trail was made for a teletype device. And these things had a bell, not the company bell, but they had an actual bell that would ring to get somebody's attention. Like if you're trying to send somebody a fax, it's not really a fax, but if you're trying to contact somebody, you can actually echo Control G to them. Control G is the bell character, and it'd actually ring their terminal. And they would walk over and be like, oh yeah, somebody's trying to contact me. Hello, how are you? And if you're logged in on the mainframe, each person has a teletype file associated with them. And if you echo things into that file, it will literally go across the network and print on their screen. And so I've locked it down, but originally when I set up the server, students were dumping the entire script of the B movie into each other's TTY devices, and it would flood their screen. They're trying to code, and all the works of Shakespeare flowing up and things like that. But there are programs like Write and things like that, and Wall. I hope you're all having fun. And then that just got broadcast to everybody on the system, and I'm on TTY 5. It looks like, okay. And then they could echo things into my terminal, and it would appear on my screen. That's how it works. So when you log in, the systemd forks itself, sets up the file descriptors, and then it execs whatever program you have in the etc password file. So if your program is no login, all no login does is exit. So if your shell is set to no login, you can't log into the server. It just quits immediately. Even if your username and password are correct, it quits immediately. And if it's bash or whatever, then it execs bash, and now bash is running. The first time you log in on the system, foreground, put that, all there is running is TC shell, because I have TC shell. So does my shell. And then when I type PS is running. And that's it. So if you want to see all the processes running on the system, you can do that. You can see there's tens of thousands of processes, I don't know, running at one time. You see Mulia is running Vim right now and stuff like that. So, fork and exec. Or fork, dupe, exec. And that's how you set up a pipe like that. Okay. So exec. Exec is the loader, basically. So you pass it, there's a lot of versions of it. You pass it basically a path name and options. Path name, and that's the simplest one right there. So you pass it a path name to the executable you want to run, and you pass it the command line parameters. And then it runs it. That's the loader right there. And so there's, when you call exec, that's where it finds the a.out or whatever, and it opens up the file, looks at the ELF, the executable loader format, and says, ah, you've got a data segment, I'm going to put that here. You got a code segment, a text segment, I'm going to put it here. You got globals, I'm going to put those here. I'm going to set the stack up here, running downwards, going to blank memory, go. And then the exec, after it sets up the memory map, the way that it's said you want it set up in the a.out, then it goes to the very first line of your code segment and starts running. And that's everything. When you type ls, that's all the different steps that take place behind the hood. The shell forks its... actually, ls might be a built-in. Okay, it's not. Okay, is it? Yeah, it's an actual program. Okay, so when you type ls, the shell forks itself. So there's now the shell's running twice. It sets up it dupes anything if you're doing a pipe command. In this case, I'm not. So then it just calls exec, passing in user bin ls as the path name to the executable, and passing in nothing as the command line parameters because I didn't pass in any. If I did pass in a command line parameter like -f and color, then that causes ls to behave differently, colorizing and stuff like that. So fork, exec, and then it runs. Exec loads this program into memory, finds the beginning of the code segment, and starts running. And the assembly just runs until it quits, until you call it exit. And then the operating system takes back over, cleans up all the memory, frees up everything once exec gets called, cleans up all the memory, deallocates all the memory, and it's good to go. And that is the life cycle of a program. What do you guys think? Honestly, still really confused. I'm kind of hungry. Yeah. I had Panera for breakfast today. I'm not going to be hungry for a while. Let me sketch it out. So, you log in. Systemd, which is the main operating system process. Systemd accepts your login. There's SSHD, and PAM is involved as well. Don't worry about it. Systemd accepts your login. It forks itself, so it continues doing its own thing. Sysd continues off doing its own thing, but it forks to form a second systemd, and then it does dupe to set up your keyboard and screen. So it sets up standard in, standard out, standard error. So systemd dupes those three things, and then it calls exec. And it becomes whatever shell you have. Bin tcsh. Okay. And bin tcsh will print to the standard output the prompt. Okay. Now, inside of here, and it reads from the keyboard and it writes to the screen, you type, let's say you type vim. So you type vim. Passing in main.cc. Bin.tcsh recognizes vim. It has a list of all the different executables that are in your path. Your path is a variable that holds all the different places where executables can be held. Vim is in your path. Cool. If you ever want to look up if something is in your path, you can use which. So it'll tell you where something is. If you ever want to see what your path is, these are all the different folders that executables can be found in. Okay. So so you type vim, the shell knows all the different executables that are in there and says, all right, cool. So it's going to do that. All right, sure. So it's going to fork itself. So it's going to stay the same. Bin tssh. The parent stays the same. And the fork is also bin tssh right now. Because when you fork it, it's the same executable for now. So you got the child fork, you have the parent fork. And then it looks at these things here. There's no pipe, so it could call dupe, but it doesn't because you don't have any pipe characters. Or if you ever did something like this, right, cat into a file, then it would call dupe. It would open the file, dupe the file to be the standard output, and then call exec. But we're not doing any of that here. We're just running it normally. So then it calls exec passing in main.cc as the command line parameter, and that turns into vim. And vim reads the command line parameters and prints the file on the screen. When vim terminates, then the OS reclaims memory. So when you call exit, it reclaims the memory. Okay. Technically, exit's not actually the ending point, but close enough. How does it know to open main.cc in Vim? You pass the command line parameter to it. So if you ever type a.out kyoto.jpg, that is a command line parameter. That's passed in argc and argv. argc is the argument count. In this case, it would be 2. And argv would hold 2 strings, a.out and kyoto.jpg. Which doesn't quite fit on the screen here. argv is an array of strings. argc is the size of the array. And so when you run your image filter assignment, when you run your image filter assignment, you can see it takes in argc. A lot of times we don't pass or don't worry about command line parameters, but for this one we do. And so argc has to be 2, a.out kyoto.jpg. And so argv is an array of strings, char star strings, C style strings, boo, hiss. And so we pass in not the first element, but the second element. The first string is going to be a.out. The second string is kyoto.jpg. And so that gets passed in here to the CImage library. The CImage library opens it. And that is right there. So when you run a program using exec, when you call the loader that way, you pass in the path name, like user, bin, vim, whatever, as the path name. And then the argv is going to be user, bin, vim is the first string. And the second string is going to be the file to open. So argc is going to be 2, argv is going to be the array of strings. And that's why file names need to be one word. Yeah. Mm-hmm. If you put a space in it, you can if you want. Vim, hi, lave. You can do it. But you have to backquote it. Okay. So when you say pass exec main.cc, it runs Vim. Did we skip a step where we direct it to use Vim? So coming back here, the user types in, so you log in, systemd forks, it uses the password file, etc password, to figure out what your shell is supposed to be. It turns itself into bin tcsh. Bin tcsh prints the prompt. At the prompt, you type vim space main.cc, hit return. So the shell takes that input, figures out where vim is, and grabs everything after that into a string. And when you call exec, the executable name gets passed in as the first part, and the command line parameters are passed in as the second part. That's the call. So you pass in the executable as the path name, and you pass in the command line parameter main.cc in argv. Does that make sense to you guys? And that's how programs run. That's the loader. The big sticky bit is the dynamic loading and things like that, but you don't need to worry about that quite just yet. So that's how ranges work. To come back from the lowest level to the highest level, that's how ranges work. So ranges work. You've got here auto const ints, so that's going to be like a initializer list maybe, or a span. Some sort of data structure holding numbers from 0 to 5. This is a lambda. Do you guys know lambdas? Lambdas are anonymous functions. This is a function with no name. The function takes one parameter named I of type int, and what the function does is it returns whether it's odd or not, or whether it's even or not. If 0 equals I modulus 2. And then square returns the square of the number. And so this is just a function called even. This is a function called square. It's just, you don't need to make a function out here. It's just a function that exists only within the scope. Inline unnamed one-time use functions. Yeah, well, kind of. You can use it as many times as you want. It only exists within the scope here. That way you don't need to pollute the global namespace with a function called even, because you might need that name even for some other thing. So it is just a function that lives just within the scope here. So the pipe syntax for ranges is pretty cool. For every, and it uses the colon here. So this is a range-based for loop, right? For every integer in ints, so the first time through the loop it'll be 0, next time through the loop it'll be 1, next time through it'll be 2, right? Except it's not, because what's happening is ints is getting transformed. And so it is getting transformed, so it only has the even elements selected out of it. Okay? So only the even elements are selected out of it, and then all of those even elements are squared, and you'll see 0, 2, and 4 are squared. So it takes this range, pipes it through a selection process where it only selects out the even ones, and then it pipes the results of that through transform, which transforms all the variables in that range into the square of their values, and then it outputs that result. Okay, and that's doing the same thing as this, except you can read this logically from left to right. You know, you take your input, filter it, square it. Whereas when you use normal functional syntax, the outermost thing, which is the transform, happens first. The inner part is the filter, and then the inner part is the square. Or, yeah, no. The inner part is the ints. There it is. So that's the inner part, and then that's the middle part, and then the outer part is around it. And so it's harder to read because you have to go like this. So that's ranges, and ranges iota. Let's see if we can get some source code on this. Yeah, so this is cool. For every integer in iota view 1 to 10. And so this is a very Python-like way of doing a for loop. So this is saying make a for loop from 1 to 10. Or 1 to 9, sorry. If you guys ever use Python, this, you know, that's typically how you do a for loop in Python. For range 1 to 5 or whatever. And so yeah. And so ranges are going to allow things to not have to require begin and end. Is there sort in here somewhere? Ranges sort. So you can sort a function, or you can sort a vector now, just by passing the vector to it. Yes! Yes! I've been wanting this for so long. It's so exciting. Mr. Bell is here. Hello, Mr. Bell. This is exciting. I've been arguing for this for such a long time. Wait, that's cheating. Vim main.mem cc. Let's say vector of ints named vec, and we'll just initialize it to 50, 20, 420, 690, negative 100, and 9000. So now we can just say sort vec. Yes. That work? Nope. Do I have to specify ranges? Sort still. Okay. Unfortunate. Okay, so there. Nope, wrong one. Maybe I should print it. For every integer x in vec, x. There you go. So that's the new hotness. You no longer need to type begin, vec.begin, vec.end. Just sort a vector. It's amazing. It just defaults to doing the whole thing. Like it should have for 10 years. C++. It should have just defaulted to the whole thing. Sorry, but better late than never. Better late than never. Okay. Better late than never. So I think you should have always just been able to say sort a vector. And if it was a container class that had a beginning and an end on it, that it would figure it out. But yeah, it's just me. So, yep. Let's see. Using equal to ranges. Can we do this? Will this work? Will that work? Sort in namespace does not name a type. Yeah, that's a function. Right. Fine. Oranges. I think I figured out a way before that you don't have to be quite so verbose, but whatever. Pretty cool stuff. All right. So we were fixing this code with magic. No, we were fixing this code using the power of Chronos, the god of time. Is ranges a new library? Yeah, it is. It is. Mm-hmm. That's new. C++ 20. Not even out yet, in depending on the implementation. So it's not a new concept, it's a library. But it's a concept also. There's also concepts. Those are new also. But let's not talk about those today. We only got 17 minutes left. So ranges is part of C++ 20. And it is a new way of being able to pipe the results of one transformation to another, to another, to another. And it's a whole new way of manipulating data structures and things like that. Probably written by people that like Python, because there's a lot of things in Python that you can do in C++ now that, I don't mind. It's fine. It's kind of like how Java, I think, had its influence as well, with all the damn verbosity in it. Okay. So it is not a new concept, just library. It's a new it's a concept. Okay. Sneak peek concepts. Yeah, not today. So this is very exciting stuff. It's very exciting stuff. All right, let's go back to the Raspberry Pi server. Do you have any of the piping here? Okay. Mr. Bell, how is life in Texas, is it? You're not muted right now. Don't have a mic? Okay. So how is the life of the professional programmer? Some of you guys might remember Mr. Bell from last year. He was my TA, and he got a job in Texas, I believe. Hopefully. How was the thunderstorm and ice storm and stuff like that? So that is actually... Did I give that to you guys? No, I didn't. Good. Because that actually had source code for all the Sepia stuff. Okay. Storms aren't bad. Okay. Being a professional programmer is a weird life. How so? How's it a weird life? What was the one I wanted to do? I got hired at a company and our software architect left and the company is kind of falling apart, but the architect that left took me up with another job and a $25K pay raise and full-time work from home, so it's a strange place. Okay, fair. But, you know, it's the... Okay. Alright. Yeah, alright. Test, let's see... So, yeah, this doesn't really have anything to do with anything. It's just going to show you guys how write works. So write is a system call, and it writes to a file descriptor. Remember, there's 3 levels of writing to files you guys know about. So far, the lowest level is system call level. At the system call level, everything is just a file descriptor. The file descriptor is just an int. So writing to file descriptor 1 is standard output. 0 is standard in, 1 is standard out, 2 is standard error. Watching businesses fall apart in front of your eyes. Yeah, but at least you got in before they fell apart, and you made friends and got a new job, so yeah, it's pretty cool. Okay. So this is going to write to the standard out, and in fact, I think there's a constant for that, but I'm just doing this to show you guys. It's going to write a string. That's why C strings are still around, because operating systems, well, at least Linux does, takes a char star. It takes a array of characters, null terminated. So you pass it a memory address. The memory address is the memory address of the H there, and then you pass in the length of the string. And so strlen will tell you how big a string is, and that will print hello world. Yeah. Right. So that is how you print using a system call. And so if you want to read about the system calls, because you'll need them for your next summer assignment, they're in section 2 of the man pages. So section 2 is system calls. Section 3 is C, standard library stuff. Section 4 is C++. Oh, wait, no, sorry. C++ isn't in the man pages. Super annoying. Yeah, I don't even know what man's. what is man section 4? It's man 4. I don't know. What man page do you want from section 4? I don't know, dude. Man 1 cat. So the first section is Unix utilities. Second is system calls. Third is, and that's useful if you're going to do like man printf, because it'll it's not going to give you the printf for C. It gives you the printf for Unix, because there's a Unix printf command. So you have to say man 3 printf if you want to look up the printf man page. Okay, so what do you guys need to know for the assignment? Man to open. So this will open a file. And man to read. Did I say vim? I said vim, didn't I? Yeah. Man to read. And so this will read from a file descriptor into a address in memory, and these are the number of bytes to read. If there are not that many bytes to read, it will read up to the maximum and then return how many were read. So which parameter? Yeah. So that is when you call open, man to open, you pass in a path name to a file you want to open. You have to get the flags right, which is super annoying. Like I said, I screwed that up last time because I don't remember which of these things are used in combinations with each other. Google it. And it's going to return a file descriptor. So when you open a file, it returns a file descriptor. Congratulations, you can now read from file 20, whatever. And then you pass that file descriptor return there. You pass that to read, pass in 20, and then you give it a memory address of your array. Do you guys remember how to make arrays in C++? .skip. And so you can just make a buffer, and you just pass the address of array as the second parameter. And then you pass in how many bytes you want to read. And that's it. And then it will write those bytes into the memory address. And then you have to use LDRB or whatever to read out of them. So none of this is in assembly. No, these are the system calls. Everything's in assembly. You don't even have a driver in C++ for this one. Everything is in assembly. Everything. There's no main. There's no main. The make file, touch main. Main is main.s, right? When you compile it, it calls ass and LD. There is no G++ in this. This is calling the assembler, and it's calling the linker directly. It's not using the GNU compiler suite at all. The reason for that is because I wanted to show to you guys you can do it without G++ if you want, but also the executables you make are tiny. That is a 1K executable, right? Whereas, I'll hit it out. 10K, right, for that tiny little program, right? So cd asm bitwise. So for this program, you have no access to C. There's no printf. There's no cout. Nothing. You have access, however, to write and read. So if you want to print something, do it yourself. Okay. The good news is you don't have to convert between integers and chars. That's always kind of an annoying assignment a lot of professors like to give. It's all going to be ASCII. It's all going to be chars. So here is how you make a program 100% start to finish in assembly. Okay. Start. Start. Not main. Start. Main is a C thing. Main is a C++ thing. So we use G++ to compile something. It's looking for a function called main. None of that. The operating system actually starts a program with start. And the reason why G++ is looking for main is because it has its own start function that does things like initializing the standard libraries and stuff like that. It's like a constructor that runs before everything else. And then once start in the clib is done, it calls main. Main's not real. Main's a construct of the GNU compiler suite. It's not actually enforced by anything. The operating system enforces _start. That's the actual beginning of the program, _start. Does it got to be start? Yes. That is what the loader is looking for. So when you have an executable, nm a.out. Start is that location in the symbol table. This thing is a symbol table. By the way, the symbol table is just a list of what functions exist in your, and maybe some other stuff that exist in your program. These are segment offsets. That is, it looks up the symbol table. When the loader execs your program, it looks at the symbol table, says, underscore start is at 000100074, sets the program counter to that number, and says go. That's where programs come from. Okay? Okay? Exec, fork, exec. Exec loads all the stuff into memory, sets everything up, finds the memory address at the beginning of the program. There it is. Sets the program counter to that address right there, says go. Doesn't care after that. That's the very beginning. Okay. So, what was that called in ASM demos? The thing that had the solution for Sepia in it? I didn't push that out because you guys had to write Sepia. In ASM demos, all the syscall stuff is in 18 syscalls. So that has all the example code you guys need to know for this. So what are you going to do in this assignment? Let me show you what it looks like after you run it. As reference. One of the worst things about moving between systems is that it messes up the permissions on everything. Chmod, everybody, can't be executable. Thank you. Thank you. Okay. There we go. So when you run it, how many letters would you like to uppercaseify? I'm going to read one character. I made this one character so you guys don't have to handle different cases. It's one character, 1 to 9. Okay. If I type in 0, it quits. Invalid input. If I type in M, invalid input, quits. So there's a little bit of vetting going on. I would like to uppercaseify 4 letters. It now is going to call read, and it is going to read 4 letters. A, B, C, capital D. Okay. You can see that it processes A, B, C, D, uppercaseify, uppercaseify, uppercaseify. If it's already uppercase, you don't need to uppercase it again. And then it is going to draw a little triangle pyramid thing because I typed the number 4 in. It prints out a 4-step down pyramid. All right, 1, 2, 3, 4, and then coming back 1, 2, 3. That's it. So these are calls to write. These are calls to read. Okay, a little bit of vetting. That's it. Hand, Walker, question? Are you going to get all break to do this? Yeah. Yeah, you're going to have until the Tuesday when we come back from break. Okay. Tonight, your image filters are due, but you're going to have like 2 weeks to do this. And it's not a hard assignment. You just kind of have to get to learn, read, and write. That's it. It's not too bad. Walker, question? Can you put 5 so you can see the pyramid? Yeah. Oh. Yeah. Goal. Right. So it only read 5 letters. You see that? Goes up by 3 each time. 1, 2, 3, 4, 5, and then down 1, 2, 3, 4. So it's a symmetrical pyramid. I got you. Okay, if we do it again with 1 letter, and I type in something that's not a letter, 9 letters, that's the biggest pyramid. Okay. So that is your assignment for holidays. That's it. So, covered a lot of stuff. We should do Bernoullian assembly. That's a great idea. Let's do chess. Maybe we should do chess over the break. Implement chess in assembly. I can make this due in 2 days, and then you can have another assignment to do over the break. What do you guys think? Yeah? All right, Alan's for it. It's 166 lines of assembly in my implementation. So, yeah, it's probably a little... Oh, I need to deploy it, don't I? Not really that bad, honestly. Sudo deploy homework, csci45. Wrong host. Let's try this again. Where'd my thing go? There you go. Sudo deploy homework, csci45, asim bitwise, and we'll look more at system calls on Thursday. So if you want to start on it, go for it. I'm getting it out early, so you guys have plenty of time to do it. But look at the asim demos. 18 has all sorts of source code to do similar things. So. Yeah, let me see what my code. There's probably a lot of comments. See, what is it? Asim bitwise dot reference then main dot s. Yeah, it has a lot of comments in it, so it's probably about 100 lines. Just eyeballing it. Maybe a little more. Somewhere in there. What is your putty launch of the quote in colorful characters? I don't know. Maybe I do now. Not all of you guys fixed your .cshrc files. When I log in as you to see if you actually did the program in assembly and not C or C++. If your .cshrc file is broken, then I fix it for you. Give you a nice colored quote. Do nothing unless you must, and when you must act, hesitate. All right, all. That is it for today. I hope you guys had a good time. Why doesn't mine? Because it's just your .cshrc file. So you can edit it however you want. And we will continue this discussion on Thursday. A lot of new C++ stuff and a lot of old stuff. We'll mix of the new and the old. And we'll continue it on Thursday. All right. See you guys.